Hello. In this lesson, we're going to talk about the properties of logarithm and the common mistakes and the application of the properties. In the last lesson, we talked about how these properties are being derived, right? For example, these properties is for exponential, okay? Exponents are involved, okay? The exponents can be positive and negative, the base can be any number as well. But in the logarithm case, right, the base has to be larger than 0 and not equals to 1. And of course, and there's a correspondence that under these conditions that the logarithm properties are directly related by the definition of logarithm. Okay, the definition of logarithm is logarithm base b, okay, which has to be greater than 0, not equals to 1 of any positive number. If that equals to triangle, whatever it is, okay, we know that number can be any real number. And that means b raised to the power of triangle, it is going to be equals to omega. Okay, so this is the definition. This is the definition. Under this definition, okay, we have derived log base of a plus b equals to log base b a plus log base b. But the second property, right? These two properties, usually we don't have any problem, but these two, actually we see a lot of common mistake, okay? Lots of common mistake. So we're gonna start by talking about these common mistake. Common mistakes. Okay, those common mistakes, for example, right? A lot of people, okay, they have the tendency to think that if this would be true. Okay, we can see obviously it is not, right? Because if a multiplication is true, then adding would not be true. So this mistake is rampant. I see these mistakes very, very often in my calculus classes, Why this is a mistake? Why this is a mistake, right? And similar mistakes, right? Similar mistakes are, okay, sometimes it could be base, it could be common log, okay? And sometimes it could be natural log. So these mistakes is made in different ways, okay? Those mistakes is made in different ways. It seems to be rather intuitive. Okay, it looks rather intuitive, right? Hey, why not, right? Log base b, a plus b, right? Log a plus b equals to log a plus log b. Or sometimes the mistake could show up like this, right? It could be any base. People tend to make that mistake. Okay, so here we're going to illustrate to you and explain to you, and I hope you have paper pencil so you see these examples and you will not make this mistake. Okay, even though this mistake looks very intuitive, it is actually terrible mistakes. So this is the general form of these mistakes, and these are the special cases we saw in the past. Okay, I certainly hope this won't happen to you and you never make these mistakes. So let's explain why this is a mistake. Okay, so we start from simple. Okay, why this is a mistake. We understand that mathematics, right? Mathematical identities, mathematical truths. If true, always true, right? True, always true, right? False once is false, right? So that's the situation. So with that understanding, then if this is true, we should be able to prove it is always true, right? If it is false, then we should have one counterexample, and one counterexample will be sufficient, right? So in this case, I like to see, for example, suppose I have a capital A equals to 2 to the power of 3, right? Capital B is equals to 2 to the power of 5, right? So I will look at this, I will look at this, why this is false, right? Why this is false. Sorry, false. Why this is a false. In this example, right? If this makes a counterexample, then I should demonstrate that the left doesn't equal to right under the circumstances. So I'm first going to look at the left, look at the right. Okay, so on the right with 2 to the power 3 and b equals to 2 to the power 5, I can very quickly realize, right, by definition, and this first one is 3, the second one is 8, right? 3, sorry, 5, sorry. The first one is 3, the second one is 5. So the right-hand side equals to, the right-hand side equals to 8. How about the left-hand side, right? So let's look at the left-hand side. Left-hand side is, A is 2 to the power 3, and this is 2 to the power 5, right? Now, okay. According to the order of operation, we have to do inside the parentheses first, and 2 to the power 3 makes 8, 2 to the power 5 is 32. So inside the parentheses, actually we got 40. So this is a 40. Does log base 2 40 equals to 8? Well, 8 is equals to log base. If you write it as log base, that's 2 to the power of 8. Okay, so 2 to the power 8 is not going to be 40. Okay, 2 to the power 8, what does that equal? Let's see, what does that equal? What equal, that equals to? It's a log base 2, right? 2 to the power 8 is 2 to the power 4 times 2 to the power 4, right? 2 to the power 4, or you can just use your calculator, okay? 2 to the power 4, okay? That's 2 to the power 8. What is 2 to the power 4? 2 to the power 4 is 16, right? 2 to the power 4 is 16. So this piece equals to log of 16 times 16. 16 times 16 is certainly not 40, right? So this number, okay, is not the same as log 2 base 40. Okay, so this identity, what it means is that this piece and that piece is not equal. They're not equal. So this equal is false. Okay, false. False once, right? It's false. Okay, so this identity, this statement, okay, is false once, therefore it is false. So that's the logic. That's the logic. Okay. So there are many similar examples for sure. There are many similar examples for sure. And so this numerical example tells us it is false. So you cannot use it. We cannot use it. But unfortunately, we see a lot of people using it. Okay, so that's why I want to give you some examples for you to reflect on and maybe relate to when you encounter such an issue. And so you don't forcefully just write from the left to the right. Okay, so the other situation is ln is in the natural log case. Because natural log is used very often, okay, because natural log is used very often, so we see this mistake very often, okay? So here, we want to explain to you with why, right? This is false, okay? So once again, I want to give you some examples, right? It's still the same argument, right? If it's true, it should always be true. False once, false, right? So I'm going to give you that case of false once, okay? So I'm going to assume A equals to E, B equals to E squared, okay? And the right-hand side, is equals to that. So I'm going to plug in the E for A and E squared for B. And we know the consequence, right? So this will equals to 1 plus 2. 1 plus 2. Okay, that's equals to 3. So the right-hand side is 3. So let's look at the left-hand side. Left-hand side is ln. Okay, ln E plus E squared. You can also use a calculator to quickly identify these two numbers are not going to be the same. And the other thing is that I'm going to write it, what is 3 equal to in terms of natural log? It's equals to ln E to the power 3, right? Remember when we did the graph, right? We have lots of these evaluations. So 3 equals to natural log E to the power 3. So now the question is E to the power 3, right? If left equals to right, that means E to the power 3 should equals to that. And that cannot be true, isn't it? Right? You can check. So the next question is, does E plus E squared equals to E to the power 3? Right? Is this true? Is this true? Right? Is this true? And if you try this on your calculator, right? So suppose I'm going to bring E, and I'm going to ask for a numerical value. Give me a numerical value. E to the power 3, what would that give me? Ask for a numerical value. So obviously they're not the same, right? So the answer is they're not the same. Therefore, if these two numbers are not the same, you take natural log, they will not be the same, right? So this tells us that once case, right? So this is not, this equals to over here, okay? This is false, okay? So this is a false. This is a false. So that is the false once case we provided, right? A false once. Then you say thus, right? Since it false once, therefore, this is a false. This is a false. Okay, and you can also make up your own examples because these properties are can be very confusing if you haven't studied it for a while. It sometimes just feel very intuitive to do it, but in fact, it's actually false, right? So let's look at another example, which is for common log. Common log is not very often used, as a matter of fact, but because of its simplicity, okay, because of its simplicity, and we're going to give you some examples to show you why this is false. Okay, so you have an example at hand, okay? So whenever you want to make that kind of mistake, at least you have some examples to say, wait a minute, let me check, right? Is this true, right? If true has to be always true, false once is false. So in this case, I'm going to take A equals to 10, B equals to 10 squared. We know 10 squared is 100, right? And the right-hand side is log 10, right? Plus log 10 squared. Okay, so that will give us equals to 1 plus 2 equals to 3. So the right-hand side is 3. How about the left-hand side? Left-hand side is log A plus B, which is 10 plus 10 squared. According to the order of operation, we're going to operate the inside first, right? So we have a common log 110, right? On the other hand, 3 is equals to log 10 to the power 3. 10 to the power 3, 10 to the power 3, we know that's 1,000. So log 1,000 certainly is not the same as log 110, right? So that's very obvious. So as a result, we know that log, right? This log, okay, so let's indicate that. So log 10 to the power 3 is not the same as log 110. Okay, then you say thus, this statement, right? This statement is false. So now we have the false once case. So a false once, right? False once, therefore this whole thing is false, right? Because we have that false once case, false once, false. Okay. The reason for these examples is such that you don't make such mistake. You don't make such mistake. Okay, so let's look at the other common mistake, right? The other common. So we have covered these common mistakes with the examples. And I would like you guys to, discover your own examples. You just need one example or two examples. So at the time when you encounter such cases, you have a second thought about what you're going to do, or at least you're going to say, you know what, I should check it. I should give it a check if that's true. And in most cases, if you can find a counter example, right? If you have a second thought, that's a good start, because then you're going to check, and then you will not make those mistakes. The second common mistake is this. Okay, the second common mistake is this. Okay, so I'm going to put it on under. Okay, so this mistake, and of course, this is not a mistake, right? This is not a mistake. But what happened is the mistake is made by people who do the following. They will put A minus B. Look how intuitive it is, right? It looks right. It looks right, but it is not. Okay, so this is another common mistake. Okay, so I'm going to remove the box because it was in the box, you know, we changed something. We changed something that is false. Common mistake. Okay, so this is another mistake. Similar mistake. Similar mistakes, of course, usually involve that, you know, you have different bases, right? They commonly use the bases, right? For example, base 2 could be used, right? And the common log may be used, right? Common log may be used. Or base E may be used, ln. So all of these are common mistakes depending on the base of log you're using. Okay, so this is the general form mistake, and these are the special case mistakes. So let's see how they are mistakes. They're terrible mistakes. They're bad, very bad mistakes. So once you make that kind of mistake, then you not only lose point for that step, you're going to lose points for the following steps. Okay, so it's a very serious mistake. So let's, once again, to give you that one counter example in your practice, so at least you have a second thought, right? At the moment you're making that mistake, well, you have some question, why this is a false, right? Why this is a false? Once again, we just have to give that counter. We just have to give that counter case, right? That false ones case, right? So I'm going to give you those false ones case for each one of these, Okay, so I'm just going to put it here, why this is false, right? So once you see those false statement, even at the moment you have doubt, right? If you at the moment you have doubt, at least you're going to check, right? Since you know how to check, and so do get your paper pencil ready and to work on these yourself, okay? And along my side, and then after the lesson, you can try your own, or you can pause the video, pause the recording, and try your own. Okay, for base 2. Okay, so I'm going to choose A equals to 2 to the power 3. The example doesn't have to be fancy, right? And you want to make it easy for you, right? And the base B is 2, right? So let's see what's on the right-hand side. Or you can start with the left, okay? We've been doing the right-hand side first, so let's do the left-hand side first. So this is equals to the left-hand side. The left-hand side, we got that, right? A is 2 to the power 3, and this is 2, and that equals to log base 2 of 8 minus 2, so that's a 6. And let's see what's on the right-hand side. The right-hand side is log base 2, right? So this is 2 to the power 3, and this is 2, right? We've seen plenty of examples of these when we're doing the graph. So these values shouldn't be too hard for us. And that equals to log base 2 of 2 to the power 3, that's a 3. 3 minus 1, right? And in the end, we get 2. 2 is equals to log base 2 of 4. Do you think log base 2, 6 and log base 4 are the same? Of course not, right? So log base 2, if you remember, this is increasing function, right? Or one-to-one functions. So when the input and output are not the same. So log base 2, 6 and log base 4, they're not the same. What does that mean? This means that the left-hand side and the right-hand side right? They're not the same. Okay, what does that mean? This means this guy is what? False ones, right? If it's false ones, it is what? It is false. You see, this is the false ones, false. Right? So all you have to do is find a counterexample. Find a counterexample. So let's look at a base 10 case. Base 10 case. Base 10 is less commonly used than base E, but it's still being used from time to time. Okay. So I'm going to give A equals to 10 squared. Okay. B, I'm going to use 1. How about that? Right? As simple as possible. So my left-hand side, right? I start from the left again. My left-hand side, that's, oh, how about we just make it 10, right? So 10 minus 1. So we get the log 9. How about the right-hand side? The simple, the better. The simple, the better. Okay, because we just want to make the point. And log capital A, which A is 10, B is 1, right? So log 10 equals to 1. And log 1 equals to 0. So in the end, we get 0. I'm sorry, we get 1. 1 is equals to log 10, right? Common log 10. And obviously, log 9 is not the same as log 10. You see, the simpler, the better. The simpler, it's easier to compare, right? And what does that mean is the left-hand side is not the same as the right-hand side in this case, in this one case, okay? So that means this piece false what? False ones. And therefore it is false. Okay, false ones, false. Okay, so let's look at the last case. I really just want to inspire some more examples that you may create for yourself so you'll not make such a mistake. Just having that second thought and verify will make a big difference, okay? All right, in this case, I'm gonna choose A equals to E, B equals to 1, okay? We wanna keep it simple. So on the left-hand side, it's just E minus 1, E minus 1, okay? Natural log E minus 1, okay? What does it equal to? I don't know. And right-hand side is that piece, right? And A is E, B is 1, right? So ln E is equals to 1, ln 1 equals to 0, so equals to 1. So we know the right-hand side equals to 1. 1 equals to what? Equals to ln E, right? So ln E should not equals to ln E minus 1, is that right? See, the left-hand side, in this one's case, it is not the same as ln E, right? That's rather obvious. And that means this piece, right? This means that piece, wait, okay? And that also means this piece, right, is not the same as this piece. Okay, and it also means that this piece false once. Okay, false once, false. So this is the narrative. This is the narrative. Okay, this is the second, terrible, second category of terrible mistake. And there's another mistake. Okay, these things usually we don't have a lot of mistake, but this one has another mistake. Okay, this one has related to this piece, we have another mistake. So let me create that mistake. Let me recreate that mistake for you. Okay, so another common mistake here is right here. Okay, I'm going to remove the box because I'm going to create a mistake. And this mistake goes like this. It goes like log base B of capital A and log base B and capital B. Look at that. Look how natural it looks, right? We simply, distribute that to the top and bottom, but it is a terrible mistake. Okay, very common mistake. And this mistake, once again, show up in different shape and form. Similar mistake. Okay, we actually don't see this mistake in its exact form, but we see in its similar form. For example, it could be 2 or 3 in multiple cases, right? It could also be showing up as a common log. It could also show up as a natural log. Oh gosh, this is such terrible mistake. Why they're terrible mistakes? Why they're terrible mistakes? Okay, so let's explain one by one. Okay, very common mistake. Okay, exceedingly common. So once again, I'm going to use why this is false. Okay. So you can pause if you like, pause the recording and make your own example to see why it's false. Because if it's false, all we have to do is to find that case, right? To find that case that once it's false once, right? So we're going to do the same for all of these 3 cases. So you have some examples at hand. Okay, so why? Okay, so in each case, we're going to find some counter examples that it is false. Okay, we need to know when it is that once it is false. Okay, so we do it one by one. Okay, feel free to create your own. Okay, so I just need to find the A and B. For example, I can have A equals to 2 to the power of 4. Okay, and B is equals to 2 to the power of 2. Okay, and we check the left-hand side. The left-hand side, we have 2 to the power 4, that's 2 to the power 4, and 2 to the power 2. Okay, and that equals to, we do order of operation. So we need to do the quotient first, right? So the top is 16, the bottom is 4. 16 divided by 4 is 4. So in the end, we're going to get what? We're going to get 2, right? Log base 2 of 4 is 2 because 2 squared is 4. Let's look at the right-hand side. Right-hand side, we have to do the logarithm first. So A is 2 to the power 4, and B is 2 squared. Okay, so the top is equals to 4. The bottom is equals to 2. And in this case, they're actually equal. Oh my God. But this true once, does that mean it's true? False once is false. Is true once is true? See, true once may not be true. Because for truth to be true, it has to be true all the time. If you find a true case, it can only say it is true this case. It doesn't mean it's going to be true all the time. So we may not have found the example. We may not have found the example because you have to prove if true has to be true in every case, right? So we're going to then so what the logic is, what the logic you need to understand here is that I actually put this example intentionally here, okay? Because sometimes you may find a case that is true, but truth once does not mean true. Only false once means it's false, okay? Because for truth to be true, we cannot be satisfied. It is only truth once. It has to be true in every case. So we're going to continue to see whether this is going to be the case, right? So we're going to continue. So I'm going to use this equals to 2 to 2, okay? And I'm going to make this to be 3, right? So I'm just going to keep trying because if that happened to be true, great, right? So this is 2. So 8 divided by 2, 8 divided by 2, you see 8 divided by 2 is 4. So this is still equals to 2. And on this side, this is going to be 2 to the power 3. And this is going to be 2, right? So what do we have? We have 3 divided by 1. 3 divided by 1. And this is 3. So truth once, false once. Okay, so what we had is truth once, false once. What do we make of it? Truth once, false once. What do we make of it? Well, as long as it is false once, it is false. Okay, so although true once, but false once, it is false. Okay, in fact, we don't have to mention that truth once if you can find false ones. Okay, let me say again. If you find the truth ones and you also find the false ones, then you don't need the truth ones because false ones, false. Okay, so that's why we write over the truth case, right? We write over the truth case. It is truth. It doesn't support our falsehood claim. Therefore, we get rid. We don't need it. We don't need it. We only need false ones. Okay. So it is false. Now we have it, right? So this piece is not equals to that piece. Okay, i.e. this piece false once. Therefore, it is false. Okay, I hope that's clear. False ones, false, but truth ones is not necessarily true because to be true, you have to be true every time. Okay, so let's look at the common law case, right? The common law case. In the common law case, we like to choose, I'm going to choose A equals to, say, 10 to the power of 3, right? B I'm going to choose it to be 10 squared. Okay, so my left-hand side equals to log, common log, and this is 10 to the power 3, 1000, right? The b is 10 squared, right? And what does that equal to? We're going to do the quotient first. And 1000 divided by 100 is 10. Log 10 is equals to 1, right? That equals to 1. So the left-hand side is 1. Let's look at the right-hand side. Okay, the right-hand side. The right-hand side. So that's our right-hand side. A is 10 to the power 3. B is 10 to the power 2. Okay, so that equals to what? 3 over 2. 3 over 2. 3 over 2 obviously is not equals to 1. Therefore, in this case, they are not the same. Not the same. And what it says is that this piece is false once. False once, false. You can see those examples are not very hard to make, but you have to think about it. You have to think about it. Okay, so false once, false. Last but not least, okay, last but not least is that for the base e, okay? So we can choose a equals to e to the power 3, right? I can choose b equals to e squared, okay, just for the fun of it, right? And the left-hand side equals to ln e to the power 3 over e squared. Okay, and that's going to be equals to ln e. Right, we're going to do the division, ln e. Ln e equals what? Equals to 1. And what's on the right-hand side? Right-hand side is that, right? So ln e to the power 3, e to the power 2. You can see all of these examples. We've seen them when we were making the graph, right? And that equals to 3/2. And 3/2 obviously is not equals to 1, right? And now we can claim that these two are not the same. You see, in writing, they look so alike, but they're not the same. They're not the same, okay? So this is not true. If this is not true, that means this piece is false once, right? It's false once. False once, it's false. False once, false. So these are the common mistake, very, very common mistake. If you don't have some hands-on experience, it's very, very easy to make these mistakes. Very, very easy, super easy to make these mistakes. Okay, so that's why it's paramount that you go through these steps and be familiar with the order of operation, okay? And so you don't make such mistakes, all right? So that's on the common mistake. That's on the common mistake, okay? So I'm going to summarize these common mistakes, okay? Just the general form. Okay, so common mistake. Okay, common mistakes, right? All of these, okay, primarily the first two. One, this is adding, that's a mistake. Okay, and sometimes this is minus, a minus b, that's a mistake. We need to remove the box, right? Because those are not true. And last but not least is that sometimes we have these things been written, okay? Log base b and be falsely being written forcibly by log base b of capital A over log base b capital B. Okay, so these are terrible, horrible mistakes that often been made by our students in the past. Okay, so don't make them. Just go through these examples, create your own examples, and yeah, make sure that, do something like that. Okay. Next, we're going to see some examples of using these properties correctly. Okay, so that's common mistakes. We've covered that. Okay, if I see more mistakes, of course we can go over them. So these are the common mistakes we've seen in the past. A lot. Now we're talking about applying these properties correctly. Okay, so I have some examples here. Okay, for example, I want to simplify, right? Without using simplify and evaluate examples to apply logarithm properties. Okay, for example, we want to simplify, right? And maybe without using calculator, we're getting a precise value, right? We'll give exact value if possible. Give exact values, okay? Typically under these titles, right? It could also be no use without the use of a calculator. Okay. Now, the use of these properties could be from left to right or right to left. Okay, it could be from left to right or left to right, right to left. It could be from left to right or right to left. Depends on the situation. You certainly have flexibility. Okay, for example, I want to simplify log base or common log 5 plus common log 20. Right? What does that equal to? Well, we want to simplify. I think of this property. So I use it from right to left, right? So the same base, 5 times 20. 5 times 20, right? And then what? That's become log 100. Log 100 equals to 2, right? So it's simplified. Another case, it could be, I would have common log 30 plus common log 1/3, right? Then what do we do? Yeah, what do we do? There are actually two ways to do it. Okay. We're gonna put these properties on, underneath, right? So this way it follows us. So we're gonna use, if we use the first property, right, from right to left, we'll have log 30 multiply 1/3, right? And that will give us what? Log 10. log 10 equals 1. Finished. Okay, but I do want to show you another way to do it. Sometime in many cases, there are always more than one way to do one particular question. Okay. I can do this. I can see this as log 3 times 10. Okay, and this one, I can see it as log 1 divided by log 3, right? So one is I'm going to use a product, and the other one I'm going to use a quotient. Okay, so I'm going to have log 1/3. Okay, I'm not going to, I didn't change it. I just, for the first step, I just changed the first one. Then I'm going to use the first property, the quotient rule, which is log 3 plus log 10 plus log 1 minus log 3. We can do that, right? Log 3 and negative log 3 makes 0. Okay, and log 10 is 1, log 1 is 0. Therefore, it is equals to 1. You can see there are more than one way to do it, right? There are more than one way to do it. You can use the product rule, quotient rule, as long as you use them properly. Okay, so let me give you another example. Okay, for example, I could be having ln of 3e. Okay, ln 3e minus ln 3. What would that be? Well, this probably reminds us of the quotient rule, right? This probably reminds us of the quotient rule. Ln minus ln, right? Something like that. So that's equals to ln, right? 3e divided by 3. That's one way to do it. And that will be equals to ln e equals to 1. Or you can use product rule on 3 times e, right? So you get ln 3 plus ln e minus ln 3. And ln 3 minus ln 3 equals to 0. So equals to ln e equals to 1. Right? So we get lots of flexibilities. Okay. Let's look at another one. Okay. So in this example, we have log base 2 of 40 minus log base 2 of 5. Okay. I could use product rule if I want, right? So this will make log base 2 40 equals to 5 times 8, right? So equals to 5 or 8 times 5. Doesn't matter which order, right? Subtracting log base 2 5. And then we can use product rule, right? So log base 2 8 plus log base 2 5. And subtracting log base 2 5. So these two subtracting, that makes 0. They're the opposite. And in the end, we get 3. Okay. And of course, you can also use a quotient rule. Right? And so the other way to do it is that we apply the quotient rule. Right? So that's log base 2 of 40 divided by 5, right? You will also get the same answer because that's going to be log base 2, 8. And that's equals to 3, right? That's how you simplify it. That's how you simplify it. Okay. I think this is enough for this set of exercise. In the next session, we are going to continue. Okay, so we're going to bring the other very interesting properties with us to our calculation, which we have derived with the inverse function situation, right? And that property I'm going to just introduce here, right? In the case, right, we understand this property. Okay, so from definition, right, from definition, we know this definition, right? We know this definition. From this definition, what we can do is that since we know the triangle is the same as this piece, right? So we can replace triangle by its equal. And that's the result of another very useful identity, okay? Another very useful identity. This identity is so useful, you're gonna see them, you're gonna see the use in calculus. But we have seen this before, right? What is the context we see this? What is the context when we are compositing functions, right? For example, we know f of x equals to e to the power x, right? And its inverse is f of inverse equals to ln x. Okay. And we know that f composite g, because these two are inverse to each other, and we have derived this, right? f of inverse of x, right? This x is going to be from the domain of f inverse, right? F inverse domain is x is greater than 0, right? So that's for ln, for the inverse. So we use this property to derive two very interesting facts, and one of them is going to be what we're looking for. Okay, so this is what we did. Okay, so we have f of, okay, inverse, right, which is ln x. Ln x. That equals to e to the power of ln x. And we know that this is going to be equals to x, right? Inverse function properties we derive from there. And we just derive it from the definition itself. And this one is the case, is a special case. This one is the special case. Because as a special case, right? When the base is e, right? When this is e, it's going to be the same. So these are the special cases. So what are the special cases, right? Well, we used to derive the following. Okay, so this is just a recap. We did that before. Now, and similar thing can be derived for any pair of inverse functions with exponential and logarithm. So I just want to indicate what is this special case. This special case, when b is 10, and this is going to be common log. Okay, when b is e, and this is going to be natural log. Okay, when b is 2, and this is going to be log base 2. In other words, right, if you look at omega, okay, omega can be any positive number, right? That's the range, right? So any positive number can be expressed exponentially by any base, provide that the base is greater than 0, not equals to 1. So this conclusion is very interesting in itself. The most commonly used one, the one that's being commonly used, most commonly used is this piece. Okay, of course you can change this to omega. If you change that to omega, this is omega. Okay, this is the most commonly used in calculus. There's, of course, there are other applications, but this is one of those very commonly used ones. And you will see in calculus, instead of putting omega there, it could be just y there. Okay, it could be y there. So that's all for this lesson. And thank you for watching. Until next time.